Welcome to the rigid body equations of motion. Today we are going to talk about the solution to rigid body problems and the Euler equations of motion. The necessary tools in order to set up and solve problems in rigid body dynamics have been developed. In the particular case of semi-holonomic constraints, one must additionally resort to the method of Lagrange's undetermined multipliers on top of the methods and techniques that have previously been developed. In order to set up the problem, we seek a particular point in the rigid body with respect to which the problem can be separated in translational and rotational parts. If we are talking about the motion of the body having a fixed point, then the point in question becomes the obvious choice and the problem is purely rotational. Otherwise, almost always the best choice is the center of mass. So in that case, the kinetic energy separates in the kinetic energy of the center of mass plus rotation of the body about an axis passing through the center of mass. And similar divisions typically hold for the angular momentum and potential energy as well. So one can then solve for the translation of the center of mass plus rotation about the center of mass in the Newtonian paradigm. So if you go back to chapter 1, the equations 122 plus 126. For holonomic conservative systems, the Lagrangian formulation is available. And in this particular situation, the Lagrangian also separates into a center of mass term plus a body term, which describes the motion about the center of mass. In either the Newtonian or Lagrangian framework, it is convenient to work in the principal axis system, where the kinetic energy reduces to the simple form given in equation 526. The suitable set of coordinates is furnished by the Euler angles, but this often simplifies if the motion is confined to 2 dimensions. For rotation about a fixed point or the center of mass, Newton's laws lead to Euler's equations of motion. We consider an inertial frame attached to the fixed point or a system of space axes with the origin at the center of mass. In that case, equation 126 holds, and as such, so we write Newton's second law down for rotational motion, and together with 486, this expands into the well-known result here, which if we put the two together, it implies that this is the form of Newton's equation relative to a rotating set of axes. So the applied external torque is equal with the rate of change of the angular momentum in the body set of axes plus the cross product between the angular momentum and the angular velocity of the body. And in component form, you would have 3 equations of this sort, where the summation is implicit only over the J and K indices. So in the principal axis system, the components of the angular momentum are given by a simple product between the corresponding moment of inertia scalar and or component of the diagonal component of the principal moment of inertia and the corresponding component of the angular velocity. So these together with 538 lead to the equation here. There is no summation over I. These are 3 separate indices, 1, 2, and 3, for corresponding to 3 equations, but we do have a summation over the J and the K indices here. So if we write them explicitly, these 3 equations should have the form given here, and these are Euler's equations of motion for a rigid body with 1 point fixed. So you see they include the applied torques, the moments of inertia, the components of the angular velocity, and also the time derivative of one of the components. Now, we have derived these in the Newtonian framework, but they can also follow from the general form of Lagrange's equations, namely the form of equation 153, written in the principal axis system. So we are looking at this particular form of Lagrange's equations, where in the principal axis system the kinetic energy is given simply by the sum here. And then we know how to write the components of the angular velocity in the body set of axes, but it is important to remember that only the only angle that corresponds to motion specifically in this coordinate set is the angle psi. So if we write the equations of motion explicitly for this angle, and so we calculate the derivatives as shown on these two lines, we immediately obtain the third of Euler's equations on the previous page. And to obtain the other two, we simply undergo cyclic permutation of the indices in order to obtain them. Now it is possible to generalize Euler's equations as follows. The angular momentum of a rotating body having a continuous mass distribution is given by this integral. And we know that the velocity for each element of mass can be expanded can be written in terms of the rotating frame as the velocity in the body frame plus this cross product between the angular velocity of the body and the radial vector of a specific mass element. So insofar we have only discussed the situation where the body is perfectly rigid, that is in the body frame, relative to the body frame, the various points of the body themselves do not move, but now we allow for this particular possibility. So if we insert this in the above expression, we have two terms which add up to the total angular momentum. The one involving the cross product is simply what we've discussed so far, but now we also have this additional term. So really we can write L as a sum of two terms. The first one is obtained from the contraction of the inertia tensor with the angular velocity, and the other one is it's an intrinsic angular momentum that is visible due to motion of a specific part of the body relative to the body set of axes. So then in component form, each component of the angular momentum is given by this kind of sum where the second term is given by this integral. And then once again using equation 486, we can take the time derivative of this expression to obtain the form here, which upon further expansion immediately leads to this result. And these are known as the Euler-Liouville equations, which are valid for quasi-rigid bodies. So for bodies where you have a slow change of at least of a part of the mass distribution throughout the body's motion. So they can be used, for example, when you study the dynamics of systems such as the Earth and its oceans, or the Earth and its atmosphere, and so on. So in summary, we have derived Euler's equations of motion for rigid bodies, both in the Newtonian and Lagrangian formulation of mechanics, and in generalized Euler-Liouville form for quasi-rigid bodies. In the following, we will discuss the torque-free motion of a rigid body. So, with that being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.